All right, class, we're going to take a look at section 14.5, talking about linear correlations. As we've spent our time talking about measures of dispersion, now we're going to actually talk about how we correlate data. Okay. So let's take a look here. We've got a wonderful formula. Of course, it's terribly large. We're going to be working through this particular formula in all its pieces, but this symbol right here means sum. So what it's doing is it's saying add up all the x's times the y's, and then times by how many there are. This is saying then subtract the sum of the x's times the sum of the y's. And so it's a very long, drawn-out formula. Here's what each individual thing says. So each one of these is actually described. So this is the sum of the squares of the first coordinates of the data pairs. And so we're going to be doing this. You can take a picture of this if you like, and we're going to work it out a little bit later. Here we go. So we've got a data spread where it says we've got a number of tutoring sessions and then their corresponding exam grades. So this would be useful information for someone like myself. If you go to tutoring 18 times, this is the actual exam grade. Hopefully it's not out of 100. But this is 6, and then 31 was their score, and then 16, and 46 was their score, and so on. And so then the data got plotted. What we're looking at now in this lesson is that we could make a line to show that there's a linear trend for this particular data, and we're going to talk about how good of a line, what should be the exact line. To do that, what we need to do is take all the data. Here are all the x's listed again here. Oops. Here are all the y's listed again here. This is the list of all the x's squared. This is the work that you're going to have to do, which I don't on this problem, but you can see this is 18 squared, this is 6 squared, this is 16 squared, this is 14 squared. So that's where all this data is coming from. Then we've got all the y's. You square all of them. So you can see this is 44 squared, 41 squared, 42 squared, all the way through. And then this is the product of all the x's and the y's. So if I took 18 times 42, that would give me this number over here. So you have to do all of this work before you can get to do anything else. Once you do all this work, this part over here, then you come down and you actually add all these up. So if I add up all the x's, I get 98. If I add up all the y's, I get 376. All the squares of x, all the squares of y, and all the x's times the y. If I add all those up, these are the numbers that are critical. These are what I have to work with. Okay, so here we go. So this is all, this whole big chart, you can see there's a lot of work built in there that I'm not working out on the video for you, but it's all just tedious work of making it happen to be able to plug into this formula. Okay, and so what we're going to do is actually take these answers that we just got, like 4,090, and put it right there. We're going to take the sum of the x's, which is 98, put it right here. And take this 376, put it right there. Here you can see the 1,396 is going to go there. The x's, the sum of the x's is this guy, that's 98, and then you're going to square it after that. Then over here we've got y squareds, so that's going to be this number. And then the y's sum right there. Okay, and here it is, all written the way that I just said it. And now the only other numbers that I didn't mention would be the 10, here, here, and here. So where did the 10s come from? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different x's. There were 10 different y's. There's 10 of everything, because back on the previous problem, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 coordinates. So the n is the number of coordinates that we have, and that's 10. So hopefully you can see the connection of these numbers, where they came from, as I was drawing arrows earlier. Now the key here is to pay attention to how it's set up. See that there's a big square root symbol down here, and then there's multiplication happening, another whole square root symbol. So it's a little bit of a tedious plugging in. If you have a nice calculator, you could just type it in just the way it is. But the next couple of animations are going to bring in the simplified version. So if I work out just the top, that'll give me 4,052. If I simplify just the inside of this square root, I get 4,356. If I simplify just the inside of this square root, I get the 4,584. If I multiply these together and then divide from 4,052, I'll get about 0.9068. Okay, so now what that will do for me is a couple things. It tells me the correlation coefficient. In other words, it tells me how well these are correlated, and we'll talk about that in a little bit about what this 0.9 means. It'll also tell me the slope of my line if I ever actually am able to graph it. So it's a very useful number, very long process to get there, but hopefully your data sets are not as big as this one, which they aren't. So it'll be a little bit better to work with. Okay, so let's take a look here. The properties of the linear correlation coefficient, as I was just talking about. If it's always a number between -1 and 1. Okay, if it's a 1 or -1, then you get a straight line. Okay? And the scatter plot is if I had plotted the data like what you see down at the bottom of your screen. If R is positive, then there's a positive correlation, like this would be a positive correlation. If it's negative, then you would get a negative correlation coefficient. So here you can see at the bottom, this is close to 1, it's a positive. Here it's a negative. Close to 0, you have pretty much no correlation happening between the two pieces of the two coordinates, the two things you're trying to compare, the data set. And I think that's everything that's important to highlight there. Yeah. There we go. Line of best fit is where we really want to go with this. And what we see is that we can take a data set that has some linear correlation and do what we call a line of best fit. Now, the actual things that we've done in probably previous years is we just kind of throw an average line out there like, oh, yeah, that looks good. But the actual line of best fit is the one that minimizes the sum of the squares of all these vertical distances. Okay, so that is a little bit of a process. So the line of best fit requires us to do these two things, which is, I think I said earlier that the slope is the correlation coefficient. I lied. It's very close. It's very similar, but you have a little bit different formula for m. So we actually have to plug into this formula to find m, which is our slope. Remember this, y equals mx plus b. This is our slope. And the b is our y-intercept. And so here are our formulas to find the slope and the y-intercept. And that'll give us our actual line of best fit, not just a regular trend line, but the actual best fit line. And so if I actually work with this data set that we were dealing with before, what I can do is find my m using this formula. And so if I want to, basically I had to do all that work that I just did to do the correlation coefficient, and then I go ahead and plug it into a little bit different formula to find my slope. So you can see I still got my 4,090 is going to go right here, times 10, and then my 98 is going to go there. And so you can see how it's all getting set up here by my 376, 10 numbers, and then times my sum of the squares, which is my 1,396 minus my 98. And so then that gives me my 0.93 when I simplify. This is actually my m. Okay. And then the y-intercept, you do a little bit different formula. You do your sum of your y's minus the m, and then times the sum of the x's, which is your 98, over n. Okay. Now, notice this is my slope, which means you need to find your slope first, and then find your b second, because we need our m to figure out what the slope was. But if I had my y-intercept, I could probably find my slope. Sounds like a problem that I don't think I saw in the lab, but could happen. And so if I simplify this thing down, I ended up getting 28.48 is my b. So that means my actual equation for this line is, if we just round, is 0.93x plus 28.48. So if I actually graph this line, I go up to 28.48, go up 0.93 over 1, up 0.093 over 1, I would end up getting the actual a best fit line for that set of data. So here we go. Let's try an application problem. Suppose there are 13 pairs of values for two variables, x and y. Use the table of critical values and the given value of the linear correlation coefficient for for x and y to determine whether we can be 95 or 99% confident there is significant linear correlation between x and y. And here R, our correlation coefficient, they can tell us it's an R, is 0.5861. So what this is doing, what it's looking at, is that because we've got this as our correlation coefficient, and there are 13 numbers, we're supposed to go to row 13 in our table of critical values. So you're going to actually get a list. It's a pop-up list on the lab that'll tell you, given this is how many numbers are in my data set, and they'll give you this. And so what it means is if I have my, so let's interpret the 0.5 and or 0.05 and 0.01 to make this a little bit more clear. So the 0.05 means that if you've got this percentage for your correlation, or this number for your correlation coefficient, then your probability of not being a linear correlation is less than 5%. So this is saying less than 5% chance, less than 5%. In other words, on the positive, you are 95% confident. Okay, that's what this would mean. And over here, this is saying that it's less than 0.01% or 0.01, which is 1%. So 1% chance that it is not linear. So 1% chance not linear. And so that's the way exactly your table is going to look. So if you're less than 1% that it's not linear, you're 99% confident that you are linear. Okay, so that's the way that this is set up. And so all you have to do is analyze your correlation coefficient based on the 13 numbers that you're looking at. You go to this particular row, whatever your n is, and you look at these numbers. So it's asking, are we 95 or 99% confident? So all I have to do is say, well, 58 is not 68, but it's bigger than this one. So what that means is that we're in this area, we are 95% confident, but not 99% confident. So we're somewhere between 95 and 99, but we say we are 95% confident for sure this is a significant linear correlation between x and y. Okay, so now we're going to take a look at actually working through a problem like this one. So you're going to look at a data set. Like I said, you're not going to have a huge one like the one that I worked through that first time, but we're going to determine the equation of the line for the best fit from this table. Data in the table at the right. So first thing that we have to do is do the work of summing the x's, summing the y's, finding their squares, and finding the multiplication of them. Notice that there's not the y squared column. That's because in slope and the b, we don't actually have the y squared. If you were doing the correlation coefficient, of course, you'd have to find that first. So a little bit more work. But here, we're going to take and just plug this in. So first of all, there's 1, 2, 3, 4 numbers. So that means my n is 4, and then the sum of x, y is over here, that's 9, 11. So we've got 4 times 9, 11, and then minus the sum of the x's, which is 32, times the sum of the y's, which is 92. It's 92. Writing it backwards. Let's write it better. So 92 here, and then over the amount of numbers I have, which is 4, times my x squareds, which is 302, and then minus my sum of the x's, which is 32, squared. Okay, so then I actually need to work this out on my calculator, which apparently I had to find, is 4 times 9, 11, and then minus 32 times 92. Make sure that you multiply the 32 and the 92 first before you subtract. And then that's, the top is 700 divided by 4 times 302 minus 32 squared. And that's going to give you 184. So 700 divided by 184 gives you 3.804. So 3.804. Right? And then that's our M. So this is M. And this will need to be reused down here. So now we just say our sum of y's, which is 92, minus our 3.804 times the sum of my x's, which is 32, all over the number of numbers I have, which is 4. Okay, so if I type this in, I got 92 minus 3.84 times 32, which gives me negative 30.88 over 4. So I divide that by 4, and I get negative 7.72. So that means my answer is y equals 3.804, or just 3.8x, minus 7.72. This would be my y-intercept is negative 7.72, and the slope of 3.804. All right, so if you have any problem-specific questions, ask me through the Ask My Instructor feature of the lab. Otherwise, good luck in this section, and thanks. You've been a wonderful class.